Thank you, everyone, for joining our session. Today, we will talk about the building Presto SQL experience on Flink. It's a joint effort between Streaming Analytics team and also Presto team. My name is Zhenqiu Huang. I'm working at the Streaming Analytics team as TM. Zhongting Hu is the Presto team PM for 2 years. This is today's agenda. I will first go over our streaming analytics use cases and also the systems and the platforms behind it. After that, I will use 2 use cases to analyze the user requirements, the pain points, and then call out the Presto SQL vision in our org. After that, Zhongting will have deeper dive into the design of our supporting Presto SQL in Flink, the solution, and also the implementation. After that, he will lay out the future work. First, I think let's go through the page first. And Uber's mission is to ignite the opportunity by setting the world in motion. Currently, Uber are operating in more than 10K cities, 93 million monthly users. It has like 5 million active drivers, and also it's operating in 600K restaurants. Uber Eats business grows very well for the last several quarters. And also the mobility business recovered very well to actually 90% compared to pre-COVID period. We also see a lot of growth in the Uber Free business. As you know that Uber business highly relies on the real-time data. So we leverage the streaming analytics to analyze the marketplace data to create a reasonable pricing model and also make the market more efficient. At the same time, those data are used to provide features to make the application more reliable, efficient, and user-friendly. So usually we classify those use cases into 4 categories. The first one is the real-time decision making. The real use case is certain pricing. Our engineers use Flink to actually analyze the supply and demand ratio, and they use that ratio to feed into the pricing model to find the right price for particular small hexagon and also in the real time. The second one is push notifications. As you can see here, let's say one Uber users, once they subscribe the order status check, in the backend, our engineers provide a Flink job to monitor those order status change and push the change into the application in the app. In the third category is actually our main use case and customers for our solution today. So it is the machine learning. So for example, the fraud team, they're using and also machine learning team and also sensing perception team, they're using Flink for the future engineering. So those data in Kafka will be analyzed by Flink using calculating windows, calculate the features, and stored in the feature store for the real-time prediction. In the fourth category is the OLAP data injection. So we provide Pinode at Uber as our OLAP engine. Flink is used as a real-time injection pipeline for the real-time data updates. We also have the updates supported at Uber. In our marketplace, Flink also uses the injection for the guidance, which is OLAP engine for the behind those use cases, actually, we have different type of systems to support them. We can see from the bottom, the first one is the Kafka and the data lake. So data ingested into the Kafka, and also by using Hoodie to ingest the data lake. In our Uber, we run the Hive as our data lake. So AthenaX on the left, query data in Presto in the Kafka, and also push the data into microservices or right into the Cassandra or our internal key value store as a feature store. On the right side, Presto is our interactive query engine. User can run ad hoc queries to explore data in the data lake, which is stored in the packet files. And also a bunch of users use Presto as a ETL, so to the data transformation and write to another table in the data lake. In the middle, the neutrino is a specialized Presto setup running on the microservices. It has the P-node connector in Presto, so that it can translate Presto SQL into P-node query language and query data in real time to serve in real-time dashboard. All those like the systems actually supporting those use cases very well. As you can see here, this is the streaming SQL use case scale. Currently, we have 2,300 pipelines in production. Actually, 80% of use case, streaming analytics use cases are using AthenaX. Those use cases serving actually processing 3 trillion data per day. Our platform provides full-night availability. And back to 2 years, we have 30% year-on-year growth. On the Presto side, we have about 12,000 monthly users. It actually handles 400K queries per day. All those queries process 50 petabytes of data every day. Our Presto team currently operating on 6,000 nodes in eight clusters in 2 different regions. And 2 of them are actually batch cluster, mainly for the ETL. This is the platform overview of our analytics org. So as you can see, data first into the Kafka, and then be queried by the AthenaX and write the P-node. The Presto, which is the neutrino, leverage the Presto query to actually query data from P-nodes and further fit into the visualization tooling for user to visualize the data. The workflow is mainly our centralized. The UWork is the centralized workflow management system, so user can drag and draw a workflow as a diagram, and then when user deploy the workflow, it will create the AthenaX job and the P-node table automatically, make the whole pipeline self-service. All these platforms help a lot to resolve the pain points of onboarding and make the engine's ecosystem easy to use and hidden the complexity of the users. But we do see some of the pain points from users. That's why we call the default SQL. Let's take a look at the 2 of these cases and to understand the pain points first. The first one is the accident detection alerts. I think this is a important feature in Uber's app. If there's any accident happens, our backend system will analyze it and report to user to provide them alternative actually chip or actually ask them to give more information for insurance purpose. So basically, those like sensor data in the phone, like the smartphone, will be actually checked by Uber and for the like analysis. Our sensing perception team leverage those sensor data to actually train the models to analyze different type of activities, and then used for the real-time prediction of the user activity to see whether it's a possible accident. Actually, in this application, user need to cover different type of analytics tools. For example, Presto SQL to explore data and to understand the importance of different features. The ETL by using Presto SQL to generate data for machine learning, and also the streaming SQL to generate the real-time features. On the right side is the Ease Restaurant Manager. User usually use Spark SQL to actually create the initial table for the upload data from Hive to P-node. And also user need to use AthenaX for real-time injection of the P-node table. In the end, user use Presto SQL for the in neutrino to actually get the real-time data for serving the data in the real-time dashboard. So in general, actually, basically, each type of application users may need to cover at least three type of SQL engines. For example, they need to first understand the attributes and also the importance of the features, or understanding the visualization of data. They leverage the Presto to query data. Once they have like basic understanding, they usually need to use Spark SQL or Hive have on Spark to generate data set for machine learning pipelines to train the model. In the end, actually, before they productionize the system, they also need to set up the Flink job or streaming SQL job to generate the real-time features, which will be used by the real-time microservice for model serving and do the real-time prediction. And lots of customers ask question about how can we translate one Presto SQL into Flink SQL so that we can create a real-time pipeline for the ingestion for the feature engineering. So actually, too many different SQL dialects in our ecosystem actually increase the actual learning curve for our customers. Besides that, we also see a bunch of UDF needs because the differences in the implementation of UDFs. For example, some Spark job, they have their third-party libraries do some data transformation. All those features need to be added in the Flink so that they can have the feature parity in the real-time pipeline. So UDF need to be created by our users for the feature parity. And also, in the SQL level, the feature parity of the streaming window support in Presto is a pain point. So that's why our org calls the Presto SQL as default SQL to actually generate to support different analytics users. So real-time analytics, we already have the neutrino for the P node, and also we have some already existing solution for the Presto on Spark. Actually, today's talk mainly focuses on the Presto SQL on streaming analytics on Flink. There's some related works on this topic. As I mentioned, Uber already contributed the P node connector so that the user can use Presto SQL to query P node data through the connector. We also have the neutrino serving as a Presto server as a proxy layer for query translation. In Facebook, they also have the POC on the Presto on Spark, which actually leverage the Spark as a fault-tolerant execution engine for the ETL workload. We also find some related work, Cora framework in LinkedIn. They basically provide a Hive query as defined as a view, and then the view can translate to different SQL dialects for Casa. They provide the interface for UDF and the common interface UDF and the compile type code gen for different engines, so that users can write the UDF once for different type of engines. All this related work inspire our solution. And then Zhongting will deep dive on our implementation design implementation. Yeah, please.
Thanks for Peter for this detailed explanation on what we're doing. So yeah, Presto SQL on Flink is one of the biggest engineering initiative that our data analytics team is bringing in the last year. So in the next few slides, I'm going to deep dive into the requirements and the implementation of the Presto SQL on Flink. So yeah, this slide, first, let's look at the requirements. When we look at the SQL on the Flink, it's originally implemented in the cloud side. And the requirement here is how we can seamlessly bring the Presto SQL dialect into the Flink. So basically, it's needed to be able to validate and validate the SQL dialect to see whether it is a supported query in the Flink streaming SQL. And meanwhile, we want to transfer some of the Presto SQL UDF implementation into the Flink as well. Also, when we look at the streaming dialect in Presto, basically we are talking about some of the window aggregation function, like hop window and tumble window. And it actually doesn't support it because Presto SQL is originally designed for the interactive and batch query. So we need to find some way to be able to support this window aggregation function in order to make a lot of SQL can be easily run in the Flink. Next slide, please. So here's a list of the technical challenges when we're looking at the Presto on Flink. So first is, these are basically two types of SQL. As I mentioned in the previous slide, the Presto SQL is designed for the interactive and batch analytics, sort of like Hive and Spark SQL and other warehouse SQL usage. And Flink SQL is actually expression language, which basically it will finally generate use this SQL to generate some and Flink job in order to run the streaming computation. So this is basically the different dialects from the different system. And also, when we look at the SQL inside a different engine, it's not only SQL itself. It also contains the system integration and also, error handling, diagnosing, and different kind of reporting. These are the ecosystem of the SQL engine. So these are pretty different from Presto and Flink as well. And also, the original purpose of running another Presto SQL and Flink is helping Flink engineer and users to be able to easily debug their SQL workload. So we are talking about, we have like a UI layout, which you can first send the Presto SQL into this UI in order to make it run in the Kafka connector. Then the user can actually do some change on the SQL in order to make sure it is a working SQL. Then they're able to using exactly the same SQL to put into the Flink engine to generate the Flink SQL streaming job. So that's sort of the end-to-end flow we are looking at. And another part is also very important is different SQL engine has different UDF. So Presto also has its different separate UDF management plugins. So we are also trying to look at a way to migrate this UDF to Flink as well. So next slide, please. So here is the architecture picture. We're looking at different engines. So if we look at pretty clearly, so that's the general architecture is pretty much the same. So basically, when a SQL goes into either coordinator in Presto or client of the Flink, it will first go to a SQL parser and analyzer. So the green component here is basically input a raw SQL string and generate a tree level structure, which we always call it as a AST, is an abstract syntax tree. So once we have this syntax tree, then the next stage is go through some logical planner to do the logical plan and also doing some logical optimization. For example, common syntax enhancement, those kind of things. So once you have the logical plan, the next phrase is going to the optimizer. And in Presto, we call it as a optimizer versus a fragmenter to generate the optimized plan or physical plan. So once this physical plan has been generated, so finally it will be able to go to the execution engine to generate the execution planner, as well as the runtime execution operators. So those operators will be finally has the code code that is generated by the code gen from the SQL. Then it will be able to build the pipeline execution engine for different engine. So those architecture is pretty much the same for the Presto and Flink, but the details are a lot of difference, right? So first is if we look at the Presto AST to the code generation, it's actually generate the machine binary code directly using the JVM bytecode generator. But in the Flink, it actually goes through the data stream planner and generate the raw Java code. And once this raw Java code has been generated during the runtime execution phase, the worker would be able to using the JIT compiler to compile this code on the fly and then generate the real machine code to be execution. So it's a lot of difference between the code generation part between the two engines. So then basically, if we want to do the translation between these two engines, for example, from Presto to Flink, then there's two ways to go. The first way is we can using the AST transformation to transfer the layout in the first layer. So this basically data structure translation. You basically generate another AST from the original AST in the Presto. So that's the first way. Another way is we can do the code generation part of translation, which basically we're still using the Presto SQL and engine to pass and do the all this kind of optimization. Then finally, it will be using the bytecode generator to generate the execution code in the Flink directly. So these are the two ways. And there's definitely a pros of cons. So if we're using the CodeGen, the absolute pros is we'll have native support with all the Presto SQL, including UDF, Lambda calculation, extra. So this is very simple in terms of the translation part. And the code generated performance consideration include the CPU and memory is also we are looking at. So whether the new generation code can be run very seamlessly in the Flink is something we need to evaluate. So, but when we look at the AST transformation, so it's basically something happen directly in the memory, and we can just using some DFS or BFS algorithm to go through the tree and generate another SQL. The implementation in the beginning is straightforward, but for some other features like UDF and the different kinds of SQL dialects translation is actually pretty difficult. So that's the pros and cons of this different approach. Next page, please. So here we come with some example. So this is basically a simple query with some predicate and some projections. So basically a simple SFP queries. From the projection, you can see we have different kinds of field we want to select. Some of the raw field and some of the field we have some UDF on top of that and some simple dialect on that, like case mandan. And once this is going to the Flink, it's actually build a data stream with a row of 4 columns. You can look at the first item here. Then after the Flink row is here, so we're going to do the object transfer to the Flink row. But in the Presto CodeGen, because it is generated bytecode according to our Presto internal data structure, which is column level structure is called block. So here we need from this translation in the CodeGen level, we need to first translate this Presto CodeGen into a Presto internal block structure. Then we need also doing the calculation, basically the code generation on this block using the Presto native CodeGen mechanism. Then finally, it needs to transfer back into the data stream, which is a row-based structure. So this, so you can from this graph is like we have 2 ways of translation happening during this SFP code generation. So this is a very simple case in the only scan filter projection. So we have definitely some complex cases like join and aggregation function and as also table function support. Next page, please. So if you recall the last graph, so it have the pros again is definitely we have completed Presto SQL dialect support, and we all fully resolve the UDF migration issues because all this UDF is just native generated by Presto CodeGen. And some of the things we need to consider is the reason that original Presto using the bytecode generation is it want to try to using the JVM compiler performance to automatically doing the optimization of this CodeGen. Also, Presto is all this worker is long running process. So all these workers would be able to cache in some of the bytecode generation in order to generate the duplicate code. So these are some optimization in the Presto, but Flink have a completely different running engines. It is running on a different containers and different jobs up and down. So it's basically cannot using this kind of optimization already in the Presto. So the another one is we're talking about in order to make this work in the Flink, we need to first translate from the raw engine into the column level data structure in the Presto, which is block, then doing the computation and finally convert it back. So there's some additional overhead during this object transformation. So basically additional overhead on the time latencies. And also, this is the same thing, like Presto is based on a block, but Flink is row-based. This is pretty much different from the batch and the real-time streaming perspective. And also this CodeGen running, we also need to think about the memory overhead because Flink is very memory sensitive, and additional this overhead will bring the more memory use, potentially memory usage from the Flink side. So next page, please. So the next few slides, we are talking about the AST transformation. So again, this is the same query we posted in the previous example. And the first graph here is what we generated in the Presto AST. So look at this is basically a tree structure, which contains the root statement like a statement and a query. And when we break down into the query spec, it has embedded a select statement and also from and projection and order by limit and the subtree node. And from the select statement, it will basically contains the different projections of the column. For example, there are going to be some row columns. There are going to be some columns based on the UDF, and there's also some sub calculation like case 1z. So in the next graph is basically the same SQL in the call side AST format. So you can see it's a little bit different, but generally it is still a tree-based structure which contains the root, which is the statement level, and break down into the select projection and the order and the filter level. So it's a different representation of the AST. Can you go next page, please? So continues to previous graph. So the goal of the AST translation is how we can seamlessly translate the first tree structure into the next one. So if we look at some of the details of this query, so the red and blue lines indicates the children nodes need to be flipping and mapping. So basically we need to look at this select subnode in the Presto. So we want to generate the SQL select subnode in the Flink. Then internally, it needs to bring down in the different mappings. For example, the row column will map into the row columns, and the different SQL case one. Then, for example, will generate the SQL case subtree in the Flink. So there's some of the mapping is going. But the complicated side is if you look at the green lines. So first, the green lines is a different SQL function. We needed to do some like UDF mapping from Presto to the Flink. And also, if you look at this blue, the blue lines, so the whole subtree needs to be flattened and flip into another internal structure in the next graph. So it's create a additional overhead over this AST transformation. So in practice, in our research, do some POC and research, we realized for the query that doesn't have really complicated AST, the translation is doable. But it's for really complicated and with a lot of nested query, there could be pretty error prone and some problem needs to be fixed. So next page. So also we are talking about the query validation. Right now, as we said, we only want to support 3 ways of interval joins, and only one layer of the native, the embedded query with the with class. And also, we want to make sure the generated SQL query can be run in the Flink 1.12 engine. So we want to validate this query by call some endpoint. Next page. And we're also talking about once we want to do the AST translation, we want to actually transfer this UDF. So there's several ways to go. For the existing UDF, we want to define some mappings, which include their parameters from Presto UDF to call side UDF. So for the new UDF that we have not supported but going to do, we are going to using some open source tools like Apache Coral, which is transport the UDF component to onboard the new UDFs for both Flink and Presto. So next page. And the next few slides, we want to deep dive a little bit with a complicated problem, which is a streaming dialect. So as we talked about before, so Presto SQL is designed for the batch and it doesn't have the window streaming window support. So when we talk about streaming window, we are generally talking about the window function like hop window, tumbling window, and a session window, those kind of things. So when we think about how we can support this, the principle is we are generally want to support this SQL dialect in the Presto by not considering too much about the performance. We want to make sure those queries are runnable query, which is basically we call it usability, in order to make sure user can interactively get some results and do the debug purpose, but not performance. So when we look at this, we also want to extend our parsers to handle these window functions. For example, the hop window, tumbling window, and the start end functions. So we are going to do a query rewrite process, which we are going to rewrite those window functions with some customized field and support those functions as Presto native UDF or window functions. And we want to leverage AthenaX to do the cross join for this window assignment for the hop window. In the next few slides, I'm going to give some examples. So next slide. So for the tumbling window, so in the left is basically which is the original Flink query. So after the SQL queries rewrite from the Presto, we generally want to generate some window function based on the schema of defined by the table start and end. And we want to do actually just flag this query into a group by different the start and end point from the tumbling window. So basically, this is just rewrite a query using the UDF versus plus group by to support tumble. So next page. So the next one is a little bit tricky, is a hop window. The difference between the hop window and the tumble window is it can have some overlap. And there's a two parameters define this. One is the normal interval, which is 1 hour, and the overlap is 5 minutes. So to do this, we want to actually have a function defined in the Presto side called window assign. This function will be able to generate the window in the two-dimension array based on the definition of this window. Basically, is 5 minutes and 1 minute. So after this two-dimension array has been generated, we're going to leverage cross-join and with AthenaX, as we talk about, to generate to flatten this two array to a table structure. Then we can do a group by to generate the hop window schema in the Presto SQL. So next page. So yeah, so that's the sort of the work we have been doing in the last few months from the last year, and in the future work. So first, we wanted to add Presto SQL as a dialect in our AthenaX, which is our internal Flink streaming platform. And we also enable some SQL in the query proxy layout. And talking about Presto DB, so the open source community is also working on the new SQL 16 front-end support, which is a natively include the streaming dialect. So going forward, we want to looking at that framework and integrate with AthenaX and Flink as well. And for the table function, which is definitely important for this window support. Right now, we're trying to using a SQL override way. But once the table function is supporting the Presto, so we probably can directly define this window as a table function in the Presto. Finally is the native support of the streaming window operators, which we, as we said, we want to support with a table plus streaming dialect. So that's the future work we are talking about. So I think that's all for this slide. And thank you very much. Very important thing is we are interactive and real-time streaming analytics group. So we are hiring very aggressively. So please contact Grish for some more opportunities. And thank you very much. So next one, let's go to some questions.